Okay. The topic of today's lecture is geometric approach to cluster varieties. And I follow the paper by Gross, Hawking, and Keel, which was written like 10 years ago, 2013, and in particular it provides geometric proof of the Laurent phenomena, which I somehow mentioned maybe months ago, and some maybe geometric explanation of what's going on. I will use some notion from algebraic geometry today. I will not use the results of today's lecture later, so this is somehow separate topic, but I wanted to add it just for completeness and maybe to understand myself better. First, I need to introduce some notations and some. So usually during today, by n, I will denote some lattice. So the word lattice means that this is a free abelian group. And I will always use two lattices at the same time. One is n, another is m, which is dual. So as a abelian group, this is a set of homomorphism of abelian group n to the z. In sense, this is isomorphic again to z in power n, but it is dual. In particular, we have a pairing, which I will denote by such brackets from n. Let me write just product to m to z. Okay, for such lattice, I will assign a geometric object, namely the torus. So this is, let me write some words like this. Torus, Tn. It can be written as n tensor c gm, or another way to write it is I'll write for a bit fancy definition, then I will explain more clearly. Spec of Cm. What does it mean? So Gm is a multiplicative group of the base field. So in our case, this will be just C star, because I always work over the field C, but in principle, I can take it. I sometimes prefer notation GM rather than C star, because GM more clearly represents what kind of structure C star I use first of all. I use structures in multiplicative group. But this is not just multiplicative group, better to say not multiplicative group, Lie group. It is a variety. So in particular, this multiplicative group, so it is a Z model, and we can take tensor product over Z of the abelian group and this. This is another way to think about it, this group. So we have lattice M, this abelian group. We can take the group ring. So this is a algebra of C where coordinates of which correspond to M. So we have for any Cm is a vector space generated by elements which are denoted by Z in power M, where M is an element of the lattice N. So big, particular Z. And of course, multiplication of such elements is standard. Z m times Z prime is Z in power m plus n prime. So if we look at this in coordinates, then Tn is just Gm in power n, or if you want, C star power n. Function and functions. So if we pick, if m has some basis f1, fn, then functions on Tn are Laurent polynomials. On this Z in power f1, Z in power okay. Okay. So I have lattice. To each lattice, I assign the torus of the same dimension, dimension equal to the rank of the lattice. And what I'm going to say is that the cluster varieties are glued, obtained by gluing such tori. But to be more, this actually already said when I defined cluster variety. But I'm going to say something more precise about this gluing. And for this, I need some generalization of the torus, which are toric varieties. But I will not, if you know what are toric varieties, it's perfect, it's great, but if you don't, I would like to say you that I will not need a full definition of toric varieties. I will need them only up to codimension 2. And because I'm going to speak about global functions on such varieties, and global functions do not depend on the submanifold of the codimension 2. Therefore, and for such definition is much easier to give. So usually toric varieties defined in terms of certain fun in N, for example. But instead, in our case, we will not need fun. We will need only its one-dimensional skeleton. So it is in our case we will have set of rows of the form number of rows can be arbitrary. I was, if we want to draw a picture, then the picture should be one-dimensional. Maybe like this. So we have, in this picture, we have 5 rows. And, this will be combinatorial data, which will define toric variety up to dimension 2. This example. And how it will look like, we have Tn and add z vi equal to 0. So let me say it as an give example for n equal 1, even a simple example. In this case, we can first consider case where we have 1 arrow. In this case, we first had C star, but then we added a point where the corresponding coordinate is equal to 0. So we get C star point where the corresponding coordinate is equal to 0. So this will be a fine line C. And similar example B. If we have in one-dimensional case there is no much choice, we can take row in opposite direction also. Then it means that we take C star, add z in power v equal to 0, and add z in power minus v equal to 0. And how do you think what we get?
P1?
Yes, we get P1. Yes. So we get C star, we get so z in power v is the standard coordinate of this P1, and it can be at point where it is equal to 0, and here z minus v equal to 0. It means 1 over z over v is equal to 0, or z in power v equal to infinity. We get P1. Maybe I left as a problem. What we get for in two-dimensional case for this beaver for fun or such. Anyway, this was a definition. So toric variety is we take is up to dimension 2 is a following. We take the torus and add such set zy equal to 0. Maybe more precisely, this should be viewed as not just as a So this is isomorphic to torus Tn quotient by V. No, T. So V is a vector in the lattice M. We can take its orthogonal complement. It is will be lattice in the sublattice in M, and the corresponding tora has codimension 1. So we have C star for N, and to each row, to each vector, we add a divisor on the infinity of the form C star in power N minus 1. And this formula explains how it is glued. Okay. Now let us return to, to the cluster story. Cluster algebras, you probably remember, were defined in terms of seeds. We had some matrix, and we had a set of initial variables, and then we mutate them and so on. Now instead of seed, we will have some instead of the matrix, we will have lattice with some additional data, and instead of variables, I'll start just from the torus, which is variables are functions. But it will be convenient to decompose the data, which we have in two parts: fixed data and seed data. So we have some fixed data which will not depend on seed. First of all, we have lattice N. Then we assume that we have pairing. Skew symmetric. Which I denote by such brackets. This shouldn't be confused with the pairing between N and M. It maps from N times N to rational functions, rational numbers. We have sublattice inside N, and this sublattice should satisfy the following property. If we take pairing between element of the unfrozen sublattice and element of the original lattice, then this pairing will be integer. I hope it is clear that this unfrozen sublattice will correspond to unfrozen vertices, unfrozen variables later. And this condition means that adjacency matrix, which we have for unfrozen variables, should be integer. we will have fixed index set I such that its cardinality is equal to rank of n. And we have corresponding subset I unfrozen. That its cardinality equal to rank of unfrozen. This will be subset. Usually it will be just some set of numbers from 1 to n, and it will be numbers of the vertices, frozen and unfrozen, or just all this. And I also keep notation m, which is home from entries. Okay. Now, what is after such preparation? What are seeds? Scene data, yes, is a collection of vectors ei labeled by index set I, such that ei form a basis in N, and ei, so here ei, here I runs through all index set, and here I runs from unfrozen set of indexes, and so hence we have a basis in unfrozen sublattice. This is just a combinatorial part of the seed. Of course, later I will say about also about variables. One can ask what is the relation between this combinatorial data and combinatorial data which we used in the original definition, and relation actually as follows. Okay. Remark. We can take matrix Bij to be the pairing between Ei and Ej. And it is antisymmetric. And what else? It is the integer whether I or J is unfrozen. Okay. Let me introduce a bit more notations. So we have our lattice N, and we have also dual lattice M. on the lattice n we had bases e1, e2, en, labeled by index set I. What do we have in the dual lattice? First of all, we can define just dual bases, which I know by fi, but maybe I can have just ei star. So EFI pairing between fi and ej is delta ej. Maybe should have in opposite order. And another notation will be vi, and this will be pairing in ei, also belongs to m. So this is a basis, and these vi generally are not bases. They are bases, only if and only if this form is non-degenerate and actually invertible. So it should have determinant equal to 1. If it is just non-degenerate, this is a basis tensor Q. And moreover, among VIs could be equal vectors. And so. But anyway, these are vectors. Okay. Now to each seed S, so one more notation. Tutorial. First, it will be two. It is standard to A and X. We have two cluster notions, two notions to cluster varieties. First is XS, which is T M or equivalently spectrum. Okay, let me just write here. And another is AS, which is T. Maybe it is a bit unexpected that from this definition looks like A and S cluster varieties, A and X cluster varieties up to now the cluster charts are dual. So we assign them to dual tools. But this is actually one of the messages of this cluster story. You have two descriptions, and in some sense they are dual. In particular, we saw this in terms of the symplectic structures. On the X cluster variety, we had Poisson structure, and on A cluster variety, we have something like symplectic or more accurately presymplectic structure. Okay. So if you want to have more explicitly coordinates, then you can take, of course, xi will be, so their xi are coordinates on this torus. So their functions on this torus, correspond to the elements of the dual lattice. So actually we don't have much choice. We take z in power ei. And for the A torus, we have coordinates ai, which are again functions of the lattice T torus equals to n. So they live in the lattice n, and they actually is in power. So here we have basis f, but also we have another vectors which I don't know by. Up to now we wasn't used, but weren't used, but I will use it. Okay, this is one chart. And now let me define mutation. First, I want to define mutation of the combinatorial data. Actually, I believe I wrote this formula sometime at some point, but anyway, so mutation, mutation will correspond to mutation will correspond to some element of the unfrozen set, so that K belongs to unfrozen set of indices. So let us define EI prime equal to minus EK if I equal to K. So maybe this should be first row. And EI plus BKI plus K. I not here I use notation. Of this. Oh goodness, this maximum. Geometrically, one can think that what happened that we had a line which is how to say we have a plane which is given by vectors which are orthogonal to EK, and on this plane everything stays on this plane. How to say it better? So you see this map is not linear. So and this is a space of vectors which are orthogonal to EK. Vectors which are okay. I'm not ready to explain geometrically now. Let me this mutation of the E vectors. F vectors, so which are bases in the dual lattice, are just dual to them. So I can write formula for their mutation. So here you see the only vector, all vectors are changed. E simply and others through EK. All vectors are changed, but only by the substitution, division, some EK. Additional subtraction, some EK. And for F, situation will be opposite because they are dual. So F I prime is equal to Fi if I is not equal to K. And for K's, vector will be something not trivial plus some by J bk j plus fg. I can left this remark that that matrix Bij in this transformation goes to Bij prime. Oh, this was a problem on some previous lecture. Or it will be problem. I don't forget you did it, published it. Right. This is a transformation of the combinatorial data. And now let me write a formal transformation of the algebraic data. So we have this combinatorial part, algebraic data. Or if you want, you can send geometric, because as I'm stating, we are doing some geometry. We have a map, okay, from X cluster variety of C dash to cluster variety X chart for C S, and similarly we have a map from A chart yes. And it is given as follows. So in order to define this map, so we should have two maps, we have two formulas. In order to write down this map, we should define how it acts on the function. So how it will act on some function z m. So xs, let me recall. So xs is a torus which correspond to m. So coordinates on it will be will correspond. Function on it correspond to elements of the lattice n. So k of zn will be zn times 1 plus z in power ek power n k. And for here, mutation formula here actually the first place where I used these v's, and actually this is the only place here where this Q-symmetric matrix, so in other words matrix B, is used. So here's the pairing between lattice and dual lattice, but Vk as a function which correspond to E. Get this one. Quite funny to know that actually this formulas now looks quite similar. If you don't quite see my indices, upper, low, so here and here we just multiply by some binomial. Sorry, some binomial in some integer power. There's of course difference. So for example, here this power is actually in both cases the power could be negative. Here this power depends on Q-symmetric forms here by pairing, but anyway, the formulas are very similar. Let me leave as a problem that this is equivalent to standard formulas. example, k star of ak prime is equal to fraction ak in denominator, and in numerator will be product of j bgk. And similarly for x. In this case, we now have system. Maybe some remark. We can compute k squared. Let us look to the combinatorial part. Okay, here is a formula for k. Let me put how it acts. So, first of all, what it did with ek. Ek goes to minus ek, and then goes to ek. But if we take other basic vector ei, then first of all it goes to ei plus bki plus ek, then it goes ea plus bki plus ek plus, now we again do case mutation, so we'll add vector proportional to the case vector, which is now minus ek, so sometimes minus ek. And what is it? This is our symmetric pairing between case vector and ice vector. Now case vector is minus ek, ice vector is ei plus some ek. Ek is ek0, so here we'll get minus bki plus this is the formula which I use, and this is equal to ei plus, so minus bki plus is bki minus, so bki ek plus bk plus. Not let me say it another. So this is equal to this. So indeed, if bki is positive, then this is 0, because minus bki is negative, and the positive part is 0, so this term bunch. And this is equal to this. And if bki is negative, then this is 0. This is positive, multiplied minus ek, so this is equal to absolute value of bki, and it gets signed here. So this is just such simple linear transformation. But what is interesting is that this transformation is non-trivial. We are used to think that k squared is equal to identity, and this is true usually. But this is not true in terms of this combinatorial data. What is true? So k squared is not equal to identity on k, but k squared equal identity on coordinates. Either xi or ai. So k squared is a trivial automorphism of the ring of coordinates on the corresponding chart. Any questions?
It also saves combinatorial part of Bij, right?
Yes, yes. So this transformation preserves the payload. I can write. Okay. And so in general, the X cluster variety X understood. X and similarly for A cluster varieties obtained maybe more accurately will be to say schemes obtained by gluing in general all excess AS corresponding which can be obtained from initial seed by mutations. Okay, this geometric diffusion. Remark. There could be many remarks here about generality and so on. Let me give this one. So quite often we do not want to convert AI corresponding to frozen variables. for this reason, geometrically, we have to redefine AS. AS will be C star in power I minus power I unfrozen times C in power I minus unfrozen. Or if you want, it will be toric variety corresponding to the R, to this set of rows REI, where I is frozen. So we add coordinate hyperplanes which correspond to frozen variables. It is equivalent to say that in the ring of functions, these variables cannot be inverted. All story about Boolean remains the same, and all definitions remain the same. This is just geometric replacement. Okay. Okay, in principle, could be more remarks, but let me move on to the geometric construction. And I will first illustrate it in the case actually of n equal 1. No, not literally, n equal 2. And then I will say that everything else is similar. How to say? But maybe I want to take back my verse about 10. So n will be arbitrary, but it will be one mutation. Anyway. So I'm going to define elementary transformation. Okay, well, what is our setting? So we have n as usual lattice. Let us assume that we have some vector v in n, which I assume to be primitive. Maybe for this reason I already noted by E. We have a projection P, which acts from n to n quotient by this subgroup generated by this vector E. Hence, we have the similar projection of the torus. Tn to Tn. In coordinates, if I think that E is just the first basic vector, And then we have some basic basis. P is as follows. It map, and I assume that xi sorry, I have to overthink. No, let me return it to V. And if I want to write down this in coordinates, maybe it was okay, but the coordinates, if we have a basis f1, fn in M such that f1 of V of E. Okay, if E is just first basic vector, we have E1, En, f1, fn dual basis. I denote by xi as a corresponding function, then the P this I x as follows. It just forgets the first chord. Okay.
Sorry, may I ask?
Yes.
What do you mean by primitive that it cannot be decomposed on sum of two positives in somehow, or what does it mean?
It means that if E is equal to some D E tilde, where E tilde belongs to N, then D is equal to plus minus 1.
Okay, I see. Thank you.
Okay, let F be only any primitive vector can be for any primitive vector we can find a set of generators of the latest such that E is equal to one of those generators. Okay, let F, it is without indices, don't be confused with this dual basis notation. Maybe I should be bad notation, but it is bad notation, but I cannot change it. Now, let F be a function on this dual torus, on this quotient torus. So in coordinates, F is Laurent polynomial on other variables, x2, xn minus 1. Then we can define then we can define a birational map mu f, which will be more or less our mutation at the end of the day, which map from the torus to itself. Make 3 more pages, just okay, sufficient for today. Which x as follows maps any point in torus t to f of pi of t inverse times t. This map is birational because this f could be zero somewhere. Laurent polynomial can have zeros. Of course, look into formulas which I wrote I forget somewhere here, for example, you can easily guess that f will be not just polynomial, but not any polynomial, but actually some binomial. But anyways, binomial can equal to 0 somewhere, so it is rational, birational. It's not everywhere defined. Depend on the open subset. In coordinates, this map acts as follows: we have x1, xn, and it maps to f inverse x1, x2, maybe you're already confused by all my notation. So actually here I missed one. You can ask what is the meaning of this multiplication. Naively, you can think, I don't know what you can think. You can think this is I multiply by number, for example. But there's no such operation of multiplication by number in the torus. This operation, this is the product of two elements on the torus, and this f is viewed as following: that we have a birational map which first acts with Tn, then to the quotient, then to C, and then it acts to so we to each element we assign a number, and then we consider the corresponding element of the torus which is generated by ZE. So it is this subtorus is a set of points on which first coordinate is x and all other coordinates equal to 1. So in coordinates, map is x like this. This is of the spirit. Like I said here, I wrote some explicit formula for the action, and in terms of coordinates, it was a standard form of notation. Anyway, maybe I should stop giving elementary remarks and proceed. Okay. Now let us consider the fun, which is just, in this case, we have only one row. The corresponding toric variety, which I denote by TV, I forgot to use notation here. So instead, TV, so the set of rows will be usually denoted by sigma. Sigma 0 TV of sigma. TV stands for toric variety. Anyways, the corresponding toric variety is just A1 times toric n over G. So in coordinates, this is a set of points x1, x2, xn. Say that x1 belongs to field, but all other points are zero. By d plus, I denote it. I denote the divisor in this variety, which is consists of points where x1 is equal to 0. Let us set z plus to be equal p inverse of the set f equal to 0, or maybe okay. Intersect with d plus. So scheme corresponding to ideal generated by f. So theoretically, this is just set of points where f vanishes. Now let us define TV tilde. Of CV plus to be a blow up of TV of sigma v plus. Blow up at this divisor C plus. Generally speaking, d plus is determined by the equation x1 equals 0, and this is determined by the equation f equals 0. Recall that f doesn't depend on x1. So this is some variety of the codimension 2, and we can take blow up here. Here we have divisor d plus tilde will be proper transform of d plus. When we can take a blow up, then we usually have some exceptional divisors, which under the submanifold where we take blow up. And difference between d plus and d plus inverse, if we take just full preimage of d plus, then it contains some components on exceptional divisor. If we exclude them, this is what's called proper transform.
So sorry, what is I don't understand, what's P or V of f? I thought it is some projection, so this preimage should be like the whole the whole TV, or I don't understand what is P. Okay.
What's pi? It is not very
Right.
important. This pi is not very important. So f is a sum function on the subtotal of x2 xn. It's it defines some subscheme which sets theoretically just zeros of f. You can take its pre-image, so it will be a set theoretically it will be a set of points where f vanishes. F doesn't depend on x1, but so we have some equation of this variable. So the plus is a set of points where both x1 and f vanishes.
Okay, so it's just pre-image of 0 in F.
Zeros of f.
Okay.
Okay. And u should be, but whatever. And now the last, for a moment, the last notation, u is tv tilde sigma v plus without d plus tilde. Maybe I'll write d mod this way. Just to have something in your head, let me draw an example. So first, we get we have toric variety which correspond to sigma e plus. So how to draw that? So we have a line, and we have I draw real picture. So maybe this line should be if you real picture would be, so it means that we have one coordinate can take arbitrary values and another non-zero, but in real picture all positive. Then we take and we have some submanifold here, which is defined by f, and in this picture it will be some point. Then we take a blow up. So after the blow up, we get some exception, some additional line, which goes here. And many other things. Get some additional line. And u plus is the thing, but without this line. Maybe I want to add one additional piece to this picture. Which will be our torus Tn. It is again something. I draw it like this, but we don't have. So here we don't have line, which correspond to x1 equals 0. So first we added line, then we picked some submanifold codimension 2 here. In this case point, we take a blow up, then we delete this line. And this is how we define this open subset. on other hand, here we have defined map mu f from one torus to another, and we can define subvariety xf scheme xf, which is gluing of two Tn via mu f. Proposition or lemma, one of the first key lemmas here, is there exists an open immersion of xf into UE plus, such that the complement to the image is codimension. Okay, I have no time to prove it, but this is straightforward. And what is the meaning of this in terms of for further application to cluster algebra? So X variety or A variety, any cluster variety obtained by gluing of the torus. And this I'm explaining how to obtain this manifold of dimension 2. We should first compactify, add something infinity, take blow up, and then delete our compactification, what we added before. This is how construction works. Okay, if somebody can ask a question, please ask.
So, what is z plus in the example? In
this point.
And d plus is line, or
yes,
or
d plus is line here, and d plus tilde is line here. Our original toric is toric variety. So, okay, now let me state another lemma. Of similar type, but now let me take another larger fun, sigma e, which will now consist of two rows. R1 is above, 1 is opposite, and 0. I forgot that I changed my notation from V to E, so please, whenever I write this small, consider it to be. Then we can consider corresponding toric variety, sigma E, and clearly it will be P1 times C star times power n minus 1. So in this case, this first coordinate x1 can now equal to 0. Sorry, can in some sense equal to infinity. It has two divisors, d plus, which correspond to x1 equal to 0, and d minus, which correspond to x1 inverse equal to. Now, let us define corresponding codimension 2 subschemes. Z plus will be d plus intersecting v. This is a definition is here, just written in a different way. Z minus will be d minus intersecting. Then we have two blow-ups. We have our P. We can take blow-up P plus. We can take blow-up P minus. Lemma. So maybe it was clear, but this blow up Z plus, and this is blow up and Z minus. Lemma. The birational map μf from xn to xn extends to isomorphism. Between P plus and P minus. Let me illustrate this again by picture. So how to draw, first of all, how to draw this pi. In this case, I draw pi like this. So we have, we added two divisors, d plus and d minus, which are given by these lines. And so in this coordinate, so in some sense, in this coordinate, we have P1, which is compact and represented as a segment. And in this coordinate, we have C star. And can actually C star and power minus 1. And we have two, these 2 points represent C plus and C minus. Then what we did, we took and these 2 points are connected by line so this line f equals this v of f. This is d plus, this is d minus. This is z plus, this is z minus. Now we take blow up. sorry. We perform blow up. What it will do? It will add us two. It will add us exceptional line here. So this will be VFF, and this will be some exceptional line for the first blow up, and this will be d plus tilde, proper transfer. And now, and here we take, maybe, yes, here should be d minus, and here we take blow up another point. So we add exceptional line here, exceptional line here. This is E, this is VFF, this is d minus tilde. And what we are saying that there is actually isomorphism between these two pictures. So this is not absolutely obvious, because you see what was one can think. So we have here open part, which in both cases is before. If we delete d plus and d minus, then this open part is just a torus. And if we delete also points where f is equal to 0, this is just a torus without where f is not equal to 0. And this is this open part here and here. But map from one to another is not identical. It is multiplication by f. But it appears that this actually maps this exceptional divisor to divisor f equals 0 here, and vice versa, exceptional divisor f equal to 0 here to the exceptional divisor. So this is maybe this is the main picture, main point of today. That what we get on the left and the right, this correspond to in some sense to two different seeds. But what the lemma 1 explained what we should have one seed. If we have seed in this case with one unfrozen variable, then the corresponding cluster variety is obtained by one blow up. And the meaning of this lemma is following: that if we have two adjacent seeds, the adjacent, it is clear that from here we have two opposite rows. If we have two adjacent seeds, then up to codimension 2, up to some details, and here just isomorphism is written, then corresponding X cluster varieties are isomorphic. So if I will go in this way for longer time, I will not do this. I don't plan to do this next time. So I just did here the theorem. A X cluster variety up to dimension 2 is just original XS plus blow-ups for all unfrozen variables, and B states the same theorem but under additional condition that if seed is totally prime. Here I should replace here replace x by a. And from this description of the cluster variety up to dimension 2, run property follows and many other properties follows. Okay, I should stop now. Are there any further questions?
So sorry, I just don't understand what is okay. Somehow some maybe motivation of just the whole last part when we took some toric variety and then took some subdivisor, some preimage, and then started to blowing it up. So.
Okay, motivation can be stated as follows. So when you look to the formula of the mutation, you get some. You see there is some binomial, and sometimes it is equal to 0. So it means that the mutation doesn't go from the tor itself. It's we should add something. But actually, the main problem is the fact that it can be 0 over 0. And for such points, mutation is not defined. If we come to 0, okay, we can just add. But the main point is it can be 0 over 0. And in order to define the mutation for such points, so this is the points where some polynomial f is equal to 0, and also one cluster variable is equal to 0. In order to define mutation for such points, we have to perform a blow-up. And this is what we actually did. So we added points where some coordinate equal to 0, we performed the blow-up, and then we deleted them, but the result, this exceptional divisor still be with us. Okay, does it make sense?
Yes, it is a bit more evident. Thank you.
Other questions? Okay, let me stop recording.